Hello everyone, and warm welcome to all of you to the design presentation of Formula Student Team Delft. We gathered here today to reveal for the first time ever the 24th addition to the Formula Student Team Delft family, the DUT24. My name is Kerem Gün. I'm the project manager of Formula Student Team Delft, and I will be your host for tonight. I'd like to start by saying thank you to everyone who is here tonight with us, our dear friends and families, and of course our esteemed partners who have made this happen with their unwavering support and trust throughout the entire journey. Our journey began on the 28th of August, and ever since then, we have been working meticulously hard to make this happen, to come up with a marvel of engineering that is the DUT24. Ladies and gentlemen, dear friends and families, we hope as a team that after tonight, you'll have a much better idea on what your sons, your daughters, your best friends have been working on for so long, for so many hours, for so many months, putting the hours in for this design. You will know at the time, after our design presentation, that this experience is truly unmatched. And the stuff you learn from this is indeed really valuable for the rest of your life. To our partners, really hope that you will take our design and the design presentation as a whole as a token of our appreciation for the support you've shown us throughout our entire journey. After this very short introduction, I will be leaving the floor to our team manager, Nick Verhoeks, who will be telling you a bit more about our team, what we are here to do, what our goals are, and also he will dive a bit deeper into the world of Formula students, so you get an idea on what the competitions are about. After him, our chief engineer, Tom Wine, will be taking the lead, and he will be telling you all about our new car, the DUT24, and he will give you an idea upon the improvements we made in our design compared to the previous years. This is the time where I tell you to sit back, relax, and enjoy as I invite our team manager, Nick Verhoeks, to the stage. Thank you.
Thank you all so much for being here. My name is Nick Verhoeks. I'm this year's team manager, and I'd like to tell you something about our year, about our team, and about the design that we made. It's been over 5 months since we started as a team, a new journey, the story of the DUT24. It's been a great time so far, and there's so much more to come. We are enjoying ourselves, amazing, and before we will go to the design, the moment you've all been waiting for, I hope to answer some of the questions you, the audience, might have. The first one being obvious. What is Formula Student? Formula Student is the biggest engineering competition around the world for students. In a year of Formula Student, you design and you build an entire Formula-style race car with a team of new students and new trained engineers. With this car, you will compete during the summer in competitions, possibly all over the world. It can be all the way in Australia or in our home country, the Netherlands, on TT Circuit Assen. We, as Formula Student Team Delft, are mainly focused on the competitions in Europa, and the main focus is Formula Student Germany. This being the most prestigious, the most high-level competition you can get all over the world, and our aim is to win that competition. A competition is about 1,000 points. A total of 1,000 points can be gained, and this is not just about racing. Next to racing, there's also a lot of other stuff that comes into play. If you're a professional race team, you don't just build a car, you think about everything. To train the engineers for also being capable in these events, they have 3 static events, the first one being a business plan presentation. This is a moment to present a business which is related to your car or your team, and the judges will determine the best business plan. A total of 75 points can be gained on this event. Secondly, we have the cost and manufacturing. We basically present our entire car in this event, and not just as a car, but in all the parts separately, and the cost and the price tag with those parts. The judges will determine if we have spent our money efficiently or that we didn't do a proper job in that sense. 100 points for this event. Lastly, the third static event is the engineering design judging. This is a moment where the industry's best people will question our engineers about our design, about our car and the systems that come with it. The questions will be about technical knowledge, design choices, and the whole process behind it. Every team prepares for this the whole year long. It starts with the first part, the first design. You want to document everything properly because they can ask all questions you can come up with. After these static events, we have the scrutineering. For Formula Student Germany, there's a 136 pages book completely full with rules. A car has to be rules compliant to each and every rule, and if it's not, you cannot compete with your car. It's only statics events if you don't pass scrutineering. It's a make or break moment for the team. If you don't do it by the books, you cannot drive your car and you cannot compete and you can most definitely not win. If you do pass them, however, you can continue to the dynamic parts, and this is where it gets fun. The first one being the skid pad. We drive 2 laps to the right, 2 laps to the left, and the average time of those laps is your final time. And you get 4 runs for this with 2 drivers, so both drivers get 1 run. We don't just do this with a driver, we can do this autonomously too. For the autonomous part, you can gain a total of 75 points, and with the driver, a total of 50. Next event, acceleration. This is all about speed. 75 meters straight down the line, quickest time wins. Also for this event, both with driver and autonomously. Then, the autocross. This is a very nice event. This event tests the car to the full limit. We will drive on the full specs, full power, to set the best lap time we can get. It's basically comparable to a Formula 1 qualification run. Only we get 4 runs, also 2 for each driver. The ranking of this event will also determine the starting order of the next event, the final event where the big points come into play. The endurance. 22 kilometers on the same track as the autocross, however, multiple runs, including a 75 points to be gained for the most efficient car. This is about the efficiency, is about the energy you spend and the time you drive for the complete 22 kilometers. All events can be won by separate teams, but in the end, the winner who gets the most points overall is the winner and gets to take the trophy home. So far the competitions. Now, our team. Formula Student Team Delft. Before I go into our team, I would like you to meet some of our team members by showing a video.
Hello, my name is Isa. I'm a Bachelor Industrial Design Engineering student, and I'm in the Operations Department at Formula Student Team Delft.
I'm Meijs van Geurp. I study mechanical engineering and I am designing the mechanical part of the electric motors.
Hello, my name is Sjoerd Nijdam, also known as Swardo. I'm currently a Bachelor Aerospace Engineering student at the TU Delft, and I'm a Vehicle Dynamicist at Formula Student Team Delft.
Hello, my name is Sjoerd Maasland. I'm currently studying Aeronautical Engineering and I'm Chief Drivetrain for the DUT24.
My name is Anton Deacon and I worked on the spring damper system of the DUT19. I was then the team manager of the DUT22 and right now I'm studying Aeronautical Engineering.
DUT is like a second family to me.
Hello, my name is Isa. I'm a Bachelor Industrial Design Engineering student, and I'm in the Operations Department at Formula Student Team Delft.
I'm Meijs van Geurp. I study mechanical engineering and I am designing the mechanical part of the electric motors.
Hello, my name is Sjoerd Nijdam, also known as Swardo. I'm currently a Bachelor Aerospace Engineering student at the TU Delft, and I'm a Vehicle Dynamicist at Formula Student Team Delft.
Hello, my name is Sjoerd Maasland. I'm currently studying Aeronautical Engineering and I'm Chief Drivetrain for the DUT24.
My name is Anton Deacon, and I worked on the spring damper system of the DUT19. I was then the team manager of the DUT22, and right now I'm studying aeronautical engineering.
DUT is like a second family to me. Coming here, working on these cars. It's currently my second year in the team, and yeah, working with these amazing people, these people who I call friends, and some of which are really close to me. Yes, DUT is definitely a second family to me. It means a lot.
For me, that means being able to experience stuff that you would never be able to experience by learning something from a textbook. You get to come across all of these problems, and together with a group of engineers that are just as motivated as you are, you get to come to solutions that you might never have thought of if you were just studying something. So that really means to me like an experience that's not comparable to studying.
It's a really motivated team, which is excited to win, and it's really nice being part of that.
DUT for me means a group of people who are really passionate about this project, working all day, sometimes even the entire night, to get a car working and finish this project which we are working on.
I like to think that I contribute a problem-solving thinking mentality, and I'm really eager to learn, which is also what the team contributes to me. I learn a lot of hands-on experience in the team.
I hope that I can contribute to a race-winning car, and in the process learning a lot, not only on technical level but also professionally.
My biggest contribution was reinforcing, or at least reminding the organization to some extent of the importance of camaraderie and teamsmanship.
I think what I'm most proud of is the fact that we're all just a group of students, and throughout the year it's such a roller coaster. You have so many challenges and problems that you have to overcome, but together as a team we're really pushing through everything, and all of the problems we're always trying to find a solution for it. And I'm so proud of the motivation amongst all of these students, that they just want to build the fastest car and are going to push through no matter what happens.
I'm proud of what we have accomplished so far, looking in the 3D model and how everything is coming right now with the parts being created. It looks really cool, and I'm really excited to really start assembly soon.
What I'm really proud of is before the DUT22 year started, at least, where I was team manager, I had a vision for how a team looks and how a high-performing team responds under high-stress situations. And then I got the opportunity to see it, at least at Formula Student Netherlands, where it was our first competition of the year. And we had planned to the best of our abilities, but we just didn't know what a competition looks like with that group of people. And so on the last day for endurance, everything you can possibly imagine went wrong, but the team responded in exactly the way that I'd imagined and hoped that they would by that stage of the year, which was communicating quickly and effectively, focusing on the problem, and all of the personal grievances and difficulties, and in a couple of occasions it was one particular person's fault. All of that was left for after the competition, when it was no longer a time-critical problem, and that matched my vision for what a team should do under those circumstances. That's probably what I was most proud of.
In 1989, a Texas professor founded Formula Student because he found that all his students, the bright students, they're so smart, but they gain zero practical experience. And what better way to teach them than racing with cars? 10 years later, 1999, DUT, Formula Student Team Delft, was founded. And 2 years later, we finished our first car. Half monocoque, half space frame, combustion engine. It actually performed very well for its first car of a new organization. It was the runner-up in the rookie division in Great Britain. Then, 7 years later, still in combustion, we won our first Formula Student Germany event, the big competition. It was founded in 2006. It took us 2 years before we got our first trophy there. 2 years later, 2010, our last combustion car, also a Formula Student Germany winner. It completely dominated the entire division, and it made a great way for us to close off our combustion time. It was a great journey with some great trophies. Next year, 1 year later, our first electric car. What they did, the DUT11, was quite impressive, incredible. First time building an electric car, immediately winning Formula Student Germany. And this was the start of something great. 2012, another electric car, another win in Formula Student Germany, making it 2 times in a row. The DUT12, the car also broke an acceleration record of all cars in the world. 1 year later, as you can see, aerodynamics made a run for it, and the cars became looking pretty cool if you ask me. But actually, with the aero, they still won Formula Student Germany, which made it 3 in a row. This is the Formula Student Germany trophy. It was this trophy in 2011, 12, 13. And since we made a hat trick, 3 in a row, we're the only ones to keep this trophy. And this one has been with us for over 10 years now. There's only 2 in the world, the other one being in Aachen, the winners of last year. And we as a team are motivated to get it and steal it from them and making it 2 next year for the DUT25 presentation. Let's move on to 2019, our first home victory, giving us the other trophy, the big one. With the DUT19, this included a world record on the wet skid pad. So overall, another great job for Formula Student Team Delft. Then, our last 2 cars, the 22 and the 23. More and bigger aggressive aero packages, even faster cars, but so did the competition. It's becoming harder to win a competition. However, we're still considered a top team. For example, last year, the DUT23 broke another world record on the acceleration run in Hungary. 75 meters straight down the line, and we managed to do it in 2.999 seconds, being the first team ever in the entire world to do a sub 3 second run. And that brings us here today with the team, Team 24. Meet the team. This was our team weekend, had a lot of fun, did some team bonding. It's a team of 95 students, mostly from TU Delft, but also from other schools. We have a complete total of 17 different nationalities, and we practice 15 different studies. We have part-time engineers, full-time engineers. You can do a minor, an intern. There's all sorts of ways, but we all have one thing in common. We all contributed to the car, the DUT24. And that's what you're all here for, the DUT24. I'm not going to let you guys wait any longer. It's time to reveal our design. It's time to reveal the DUT24. Thank you. I mean, wow, what an amazing car. So now that we've been introduced to these competitions and our team, we're finally ready to actually talk about the car, the design, and how we came to it. But I first want to talk about some obstacles that we faced along the way and that we needed to solve to actually make a race-winning car. Because what we've seen over these last years is that not the theoretical performance is limiting, but really putting this theoretical performance out there, both on the competition and realizing it during production phase. So these actual obstacles that we've determined are, for example, resources. So the first that we call traditional resources are just finances. Finances, parts, goods, whatever you want that you need to design a car. For this, I really just want to thank all the sponsors. You really make this possible. And also, without you, our car would look very different. So if we had unlimited budget, our car would be different, but also if we had very limited budget. And other resources are just facilities. We need to be able to test both the car itself, but also panels, designs, etc. And the last resource that's also very important is actually knowledge. Because don't forget, we are all students. We are not race engineers. And we need all the knowledge we can get, both on designing, but also how to run the team. And for this, I really want to thank all the alumni that have helped us, both in guidance this year, but also for doing all the designs over the years and giving us this knowledge. Because without them, we would have a really other start. And the other one is reliability. We really have seen, again, that winners of FSG and other competitions have gotten almost all the points. So around the 80–90% mark of all the points, which means that you have to do all the events, you have to finish them, otherwise you can never reach them. But also that consistency is key. You need to be able to get all the points and be first, or at least podium on all of them, to make a chance at winning. So you not only need to have a reliable car, but you also need a fast, reliable car. You need to do all of them at the same time, which frankly is just pretty hard. And it's really what we designed our car around. And the last one is time, because we only have 1 year to both learn how to design, do research, analysis, then actually go to designing, production, assembly, then testing, and then racing. So we really need to balance out all the time that we have, look at all the phases, and just plan around it, because we need all the time we can get. And there we go back to the reliability again. Because if you finish your car in production a day before competition, you will not have a fast car because you've never tested it before. It needs to not only be theoretically fast, it needs to be fast in real life. So you both need to go performance testing, but also stuff just starts breaking. And if you don't test them, then they'll break in competition, which means, again, you don't finish your events, and you will not have a fast car. But yeah, then we go to the actual designing, which is what all our engineers have worked on for this last year, or the last 6 months, sorry. And to start with, for a car, you need a frame, which is, in our case, a chassis. And the chassis is made from carbon fiber. It's a carbon fiber monocoque made from sandwich panels, so there's aluminum honeycomb in the middle, and then an inner and outer skin from carbon. And we do this because we need a frame to both protect the driver and components inside, but also to attach all the other components to. And this needs to be both strong and stiff while still being lightweight, because it is a race car after all, which is also why you see all other high-end race cars to have a carbon fiber monocoque. And we've also gone for split molds, which means that the top and bottom of the chassis is split, so we can laminate both at the same time. This both reduces production time, which again gives us more testing time, which means a faster car overall, but also just reduces the errors in laminating, because it's a lot easier to reach, which again means you both have a more high quality car, but also you should have less time to fix stuff, which means again a faster car. Well, you now have a chassis, a frame, but this frame, to be considered a vehicle,
needs to roll, which is why we're going to drivetrain, because our tires need to be able to roll, which is why we've again looked at the planetary gearbox that we have, which makes the motor be able to roll the wheels. And we've redesigned it, because this is both unsprung and rotational mass, which is very performance critical. And we've been able to reduce each wheel by about 200 grams, which is in total of 800 grams. And again, because this is rotational and unsprung, this really increases the performance a lot. And to attach our tires to this gearbox, we also have carbon rims. These we design and produce in-house, all by our engineers. And these carbon rims, they are 1.5 kilos lighter per rim than standard magnesium rims that you can buy for these, which again is a massive performance increase for our car. The last one is our increased brake stiffness for the whole system. So we've both looked at individual components and the pedal ergonomics to be able to make it a lot stiffer. This just gives a lot better driver feedback. You've probably driven a car with a mushy pedal before. It just doesn't feel that inspiring, doesn't give you confidence, and the driver needs all the confidence they get. It also means that you need less travel to be able to actuate the brakes well. And for this, because we have an autonomous car, we have a pneumatic brake system that can stop the car in emergencies during autonomous missions. And because of this less travel, we've been able to implement a fluidic muscle, which is basically just a fancy tube, which, if you put pressure in it, expands in diameter and contracts in length. And because of this implementation, we've been able to save a lot of weight. Together with our carbon fiber air tanks, some regulators and connectors, we've been able to save 1.5 kilos, which compared to last year is a save of 50%, which again, because we have such a light car, is a lot. So now we have something that rotates and a frame, but it still needs to be attached to each other. And we will not just attach it rigidly. One, it's not allowed by the rules, but also we need to be able to optimize our tires, because our tires just give the most performance, because they give you the grip that you need. Which is why suspension has made the the optimized wheel path such that the tires, are just used to their full potential, so we can drive really fast. But the problem with this is that drivers have both different weights, there are different tracks, and they have different preferences. So we've implemented shims, so we can tune a lot of parameters on this suspension. And with this tuning, we can both fine-tune it for the driver and for the conditions. And again, this should make the car a lot faster. And we can also optimize between the different events. And the last one, again, because we want to be able to compete in autonomous events to get all the points, we also have an autonomous steering system. This really is just a motor that's attached with a ball screw to the steering rack. And we use this to be able to actuate the wheels to steer, so we can do all the driver's events. So we now have what we call in Dutch a zeepkist, or a soapbox, because now we just only have a frame with some rolling tires that we can push. So we need some actuation, which is powertrain. And this year again, we have a four-wheel drive wheel in-hub car. So what we do is we put the motors, instead of in the chassis like a normal car, we put them inside the wheels. So then we can reduce both the weight, but also just have more control. And we have around 4 times 35 kilowatts, with a total of 141 kilowatts that go to the wheels. And this is just really a lot of power that is used. And with this power comes a lot of heat, which is why we have our own custom cooling motor housings. These are 3D printed with integrated cooling channels in them, which means that we get a lot more performance in cooling, which means we can use a lot more power, and it also just is relatively light. And to be able to control all this power, we have our own self-designed motor controllers. These are self-designed, partly self-built, and these are, compared to industry standard, a lot more efficient. So we just use less energy, and we can switch faster. But even with this efficiency increase, we are still 65% lighter and a third of the volume compared to industry standard. And this gives us both, again, a advantage in weight, but also in packaging, which means our chassis can be smaller. We can put it easier in the front, the rear, wherever we want. So just a lot of advantages to these. So we have a lot of power. We have a rolling chassis. So what do we need? So we still need to go put all this power down. And for this, we've put in a massive aero package. And we've really focused on both high downforce, but also stability. Because high downforce doesn't mean much if it disappears with a bit of side wind or a bit of roll of your car. So we really have simulated a lot of scenarios such that we can reach this high downforce everywhere on the track, and we can always have a fast car. Next to this, we've also looked a lot into efficiency, and this efficiency has been increased by 9%, which just means that, one, we are more efficient, we get more points on endurance on the efficiency category, but also our battery can just be smaller, and our cables, etc., can also be smaller. And the big result of this is a downforce coefficient, which is CLA of 6, and a drag coefficient of 1.8. This probably doesn't mean much for a lot of you, but with these coefficients, we can drive upside down at 94 kilometers an hour. So basically, we can drive upside down at less than highway speeds, which is frankly really impressive. But with this massive aero package, we also get a lot of drag. Like so, 1.8 doesn't mean much, but this means we've implemented DRS, which is a drag reduction system. And just like in Formula 1, we can move the elements on the rear wing to be able to reduce this drag. And we've been able to reduce it by 44% from 1.8 to 1. And this also means that we both use less energy, which again reduces battery size. But also means we can just reach higher top speed on straights, and this also increases performance. Next to this, they've also looked directly at the weight, and they've looked at the side diffuser. They've hollowed out the side diffuser, just removed a lot of foam, and this saved 1.4 kilos, which again, on our car is a lot. So we have a lot of downforce, we have grip, we have power, but we cannot just use this power. We need software and controls for that. Again, because we have so much power, if we just give it gas without any controls, we just start spinning and slipping just like you do on an icy road, which is why we have our own traction control system. And with traction control, because we have 4 wheels, we can also send different torques to all these wheels, and then we can do torque factoring. So if you have looked at videos of tanks before, they can just rotate around their central axis, and we can basically do the same, which we use a lot for low-speed corners, really tight corners, which you can almost turn around in. And also with this torque factoring, we're able to produce the right amount of torques on all the 4 wheels. So we just have a massive amount of control on all the wheels, and thus we can use all the grip we have. And because there's so much software and controls, we also do live telemetry. So we can look at all the data, we log all the data, so we can do improvements on this. So we can look at, oh, do we have too much slip, do we have too little slip, etc., to optimize all this control, and again, make it a faster car. But for the software, we need a brain, which is why we have electronics. And these PCBs, or electronics, we design ourselves. We also partly produce them in-house. And this just gives a lot of advantage, both in custom software, but also in space and weight. We can just really tune our electronics for our application, which really has a lot of advantages. And our key component of that this year is our self-developed BMS, which is the battery management system, which we use on our low-voltage battery. And we do this, one, again, because of the weight and the size, but also because then we have a lot more control over our LVB. We log a lot more data. We can have a lot more in-depth look in what happens to our battery. And this also can take more risks and just can use the battery a lot better. So now we have a fully functioning car. We have a fast car. but it's not designed yet. We just know what's going in there, which is why we have our vehicle dynamics department. So this vehicle dynamics department does a lot of simulations on our car. They simulate how fast it goes, how many theoretical points it will gain for this. And we use all these simulations to be able to make trade-offs for the departments. So if we wouldn't have vehicle dynamics, every department would just prioritize their own thing. So aerodynamics would get the most downforce they would ever want. Suspension would do a lot of weird stuff. Chassis would be really heavy to be CES compliant. And somebody needs to be able to actually say, what is the right design choice? What path do we take? And where do we go from here? And the problem here is that these are all models. And models are not real life, which is why we look at a lot of real life data. So like I explained before, we have live telemetry. We log all of it, which means that we can compare our models to what actually happens in real life and adjust the models to this. And this again makes sure that we are going to the most high performance car that is within our design reach. And like Nick also explained, we also need the points from the autonomous event, because there's still a lot. And we now have all the mechanical sides of it, but we still need the software side of it. Because, yeah, we have the actuations, but somebody needs to actuate those, and that is autonomous. And the first thing we need is actually eyes. So that's the LiDAR in our case. So the LiDAR looks at our track, and there's a lot of cones on them. And it tries to look where we are and where we need to go. And then autonomous computer starts calculating the optimal path for them. But for the LiDAR, we also have a neural network that looks at all the images and data we get, and then uses it to identify all the cones. Thus, we have an actual map, and then we have a track that we can follow. And then the autonomous computer starts building the most optimal path it needs to take and adjust itself. But of course, what is the optimal path? This is also one of the critical things in autonomous, which is one, making controllers and simulating them again with models to be able to see what is their performance. And that's where we're able to drive autonomously on all the event, or on the skid pad and acceleration event. And that's where we have our final car. And our final car should have a weight of 170.3 kilos with a total power of 141 kilowatts. This gives us around a 1.1 horsepower per kilogram power to weight ratio. And if you compare that to other cars, this is about the same as a Rimac Nevera. And for you don't know, that is a multi-million-dollar hypercar that currently has the electric production car 0 to 100 acceleration record. So it's really impressive that we as a student team can match those numbers. Next to this, we have a 6 CCLA. So not only do we have 6 CCLA, but also in cornering. And together with a drag coefficient of 1.8 CDA, which is the drag, we're able to reach 0 to 100 in 1.78 seconds. And again, putting this into perspective, the Rimac Nevera does this in 1.85. So this is mind-blowingly fast, but we have another trick up our sleeve, which is we can do it autonomously, which then we do 0 to 100 in 1.55 seconds, which again are times you only see on drag strips and not really in real life. Next to this, with our arrow, we can also put 2.5 Gs in lateral acceleration. While this might seem low to some car enthusiasts, do keep in mind that we don't go that fast. Our top speed is 130 kilometers an hour. And for example, other cars, like a Formula 1 car, does about 4 to 6 Gs, but they do it at way higher speeds. So this really just is an impressive number. And for this, I want to invite Nick and Kerem onto the stage, because this is our actual design. Then
Thank you, Twan. This brings us to almost the end of our presentation, but there's one very important thing left to say, which is our team goal. To win FSG, with a complete, well-tested and high-quality car. Thank you.
Thank you, everyone. Well, thank you, everyone, for joining. Hope you had a really nice time here. Thank you. Hope you enjoyed the show. We really enjoyed ourselves. And now we're going to invite everyone to have some drinks, enjoy some drinks with us, and talk to our team members downstairs. Thank you.